Welcome to Characteristics of Video Streaming. So today we're going to look at the characteristics of video streaming from the AS level syllabus, and I'm going to look at an exam question at the end as per usual. So if you're not already, subscribe to my channel, please like my videos, and teachers, you can visit my shop on TESS and follow me on Twitter. So here's a brief history of video streaming, or a brief history of videos in general. So firstly, the first videotape recorder was developed in 1951, captured live images on TV cameras. So it converted basically the electrical pulses, saving them onto a magnetic videotape. Then after video recorders dropped significantly in price, because that was always the way in terms of holding back technology, would be how expensive it is. VCRs went on the consumer market in 1971. So then there was the invention of the DVD. So the use of digital techniques brought the DVD in 1997. And then there was the release of Blu-ray in 2006, where videotapes basically plummeted very, very quickly, because there was so many advantages to DVD and Blu-ray, with much clearer picture, better quality sound, and no need to rewind the tape so you can, to watch the film. Now we're in a digital age, and I can honestly say I think I might own one DVD that I don't even watch, which is funny, considering obviously that I was a teenager in the 90s, and I remember having stacks of DVDs and obviously videotapes as well. Now I stream everything, so we're in a digital age. Technology is inexpensive, and it allows us to capture and store and edit images on all devices. So for example, you can edit a whole video using your mobile phone. Lots and lots of people stream from Netflix and various other sites. So the digital age, as we were talking about, Netflix has reduced the cost of video production, and it is now completely tapeless. So digital broadcasting appears on many platforms, not on just on TV. So for example, you can access Netflix on your laptop, on your tablet, on your smart TV, even on your phone. So let's look at the characteristics now of video streaming. So a number of frames basically per second run through a video. So when stuff was actually filmed onto tape like this, each one of these that I'm pointing at right now is a frame. So we're looking at interlaced and progressive encoding, aspect ratio, color space, bits per pixel, video quality, and compression methods for digital video. So frames are simply still pictures. Basically what we're seeing is an illusion. Okay, so the picture isn't actually moving, it's just frames or images or photos, if you like, that are actually flicking through the screen. So still, basically, these pictures still move at a rate of around 6 to 8 frames per second, but for older and more mechanical cameras, they went around much quicker, around 120. So now, the frame rate standards in Europe, Asia and Australia is known as PAL. Okay, and then we've got SECA, which is France, Russia and parts of Africa. They are around about 25 frames per second. So the NTSC standard, USA, Canada and Japan, are around 29.97 frames per second. And to achieve a more comfortable frame rate for an illusion of an image, it must move around 16 frames per second. Why the standards are different around different parts of the world, I don't know, but one thing I do know was, for example, if you went and bought a DVD or a videotape from USA, it would not work in England, and that was probably the reason why. Now, interlaced and progressive video scanning. So you can see the images here. Okay, so they should give you a clue. So with interlaced, This is a common way to compress videos. Okay, very common. So each frame of an interlaced video signal shows every other horizontal line on the image. Now, the images from the frames are projected onto the screen, and the video signal alternate between the odd and even lines. So you're probably thinking, well, why do they do this? Well, if they try to send in image by image, then you'll basically get lots of buffering, and it will be very slow moving. So when played at 60 frames, the image is smooth to the human eye. So that gives us the illusion of, you know, a crystal clear film that you're watching. So now analog TV in Europe and USA, okay, used interlacing for decades. So the advantage of interlacing is because only 50% of the frame is sent, so it uses half the bandwidth when sending the picture. So the disadvantage of interlaced video is that the fast motion can appear slightly blurred, so as you can see right here. Now DVD and HD TV support progressive scanning basically to prevent this, so you can see the progressive scanning here. So progressive. Now the video signal draws a line of each of the pictures, and whilst interlacing it alternates between odd and even lines. So the progressive draws the line in sequence, results in twice the amount of bandwidth needed to send the video. So although interlacing produces less flicker and uses half the bandwidth, progressive scan refreshes at 32 Hz where the interlaced is 60 Hz. So basically, you know, you can already see this produces far less bandwidth. Now, continuing progressing, if the interlaced and the progressive were both projected at 60 Hz, the progressive scanned images will be clearer, which I know is difficult to see in that picture, but they would simply be clearer. So when you see formats basically of 480p or 1080p, then the P actually indicates progressive. So, and the I will indicate interlaced. Right, so now moving on to aspect ratios. Okay, so the images here should give you an indication. So the aspect ratio just simply describes the dimension of a video screen and the video pixels. So all common formats are rectangular in shape and are described by the ratio in the width and the height, okay? So now, as we said, common formats tend to be rectangular. So now, compression techniques and packaging of multimedia content. Okay, so obviously, you know, you filmed this. We can see here that there's different aspect ratios. This would be, you know, like the classic TV here that don't really exist anymore. Then you've got the cinema screen and you've got your HD TV. So, well, this needs to be compressed and it needs to be streamed to you in front of you. So, now it has to have a file size reduced to allow the content to be transmitted quickly and smoothly with minimal loss of data. So, if you filmed an amazing film, an amazing TV series, like you can see some amazing stuff on Netflix where, you know, the costumes are fantastic, you know, the sets are very colourful and very stylish. Well, you want to stream that and you want people to watch it. But with every depth of colour and every pixel of those images, well, will come large file sizes. So obviously the file size will need to be reduced with a minimal loss, obviously, to the colour and the quality of the picture. So there's two ways. Okay, so we've got a lossless compression where the file size is reduced but no data is lost, and as we know, the process can be reversed. And then we've got the lossy compression where the file size is reduced with a loss of data, and obviously it can't be reversed because once the data is being destroyed and lost, it can't come back. So here's an example. So we look into Huffman coding. Okay, so it's a detailed but simple coding method where the codes are most often used basically in letters and text files with a shorter code. So you can see here that, you know, the letter A, I, O and E are basically vowels that are used in the English language all the time. There's going to be lots of them. Okay, so then they're just given a shorter code and repeated. then the lossy compression is where run length encoding is lossless. So then it can be reversed, because what they do here is with run length encoding, they just count how many times, for example, a colour will come up. And then lossy compression will remove the sounds and the images that the human ear cannot hear and the human eye cannot distinguish. Okay? So, run length encoding. Here's your scenario. So you're standing outside your house and you're telling your friend the colour of each car going past. Okay, so we've got red, yellow, blue, yellow, blue, and so on and so on. So that's how you would say it, how I just said it there. But what run length encoding will do is that it just simply descends it down. So it says there's 3 red, 4 yellow, and 2 blue. So it takes up, less memory, and it's lossless. There's been no data lost at all. So it's just found a very efficient way to actually encode those files. So this is used in filming. So as you can see here, for example, 4 minutes of a scene filmed at a beach. Okay, so you can see the colours here are all the same. You've got yellow for the sand, you've got some green for the trees there. The sky's blue with a few clouds, and there's some blue in the sea. Okay, so there's similar colours on the screen for the duration of the shot, and 4 minutes is a long time. Okay, so you've got the blues of the sky and the sea, and the yellows of the sand. So each frame would contain similar data so that the file doesn't need to record all of the colours each time. So the compression software will understand this, because it's quite clever. Seeing the same colours over and over again, it can recycle some of the data using run length encoding. Okay, so we can apply these to images. So assuming there's 8 bits per pixel, and then you've got 38 pixels, so that's equal to 38 bytes. RLE will store and count the value of each run. Okay, and there we go. So that will equal 16 bytes. Okay. Now, spatial and temporal redundancy. So now what this is the elements are duplicated within a structure, such as pixels in a still image and bit patterns in the file. So it exploits the spatial redundancy, and it's how the compression is performed. So in contrast with temporal redundancy. So temporal redundancy is when pixels in 2 video frames that have been the same values in the same location. So how do we tackle this in compression? So the elements are duplicated, and the pixels is basically there, and then the 2 frames that have the same values in the same location. So when using coding techniques such as RLE, the temporal redundancy will change frame by frame, coding and recording the differences between the adjacent frames. And the video contains both images and sounds, and the images and sounds must be dealt with independently so they can be synchronized. So the spatial redundancy uses techniques that is applicable to the images and the files, such as the reduction of color depth. Right, let's take a look now. So we're going to look at some, now what I'm going to do actually, I'm going to type these out because, as you know, my graphics tablet is pretty awful. Okay, so I'm just going to get here. So we're going to describe interlaced code encoding, right? So it's 3 marks. Okay, so there's probably 3 points that you might want to come up with. So if we was to think about our interlaced encoding that we just discussed earlier, what would we put in this exam question? Okay, so now I would think of a fair few things. So where should we start? It might be a good idea. So it says, now, so if we sit here and think, you got 1 frame, what do they do with interlaced? Okay, so it gets the data from a single frame and it splits it. Okay, so I'm just going to put these into bullet points for you. So data from single frame and splits it. Okay, Right, then I'm thinking, well, what does it do after that? So if you remember, so it splits the data into these like single frames, and then, sorry, it splits it into two separate fields basically. So then it alternates. So basically what it does is that one field would be odd and one even. Okay, sorry, forgot to put there we go. Oh, still managed to miss the L on a keyboard. Okay, so now basically from there it alternates. Okay, so it alternates between the two. Okay, and then it sees, and then obviously the viewer sees this all at the same time. Okay, so that's one way you can answer that, but obviously you wouldn't put in bullet points like that, you'd answer in full sentences. So now the next one, it says state one benefit of using interlaced encoding compared to progressive encoding. Right, so if we said earlier, for example, we said about picture quality, okay, and also the interlaced encoding, so it basically needs a lower bandwidth. So lower bandwidth, okay, and if we remember what he said, it plays the images smoothly because it has a higher refresh rate, okay. Well, it's two things you could say, but basically we could stick with here lower bandwidth. Okay, now next thing. Right, so it says about how a video can be compressed using spatial redundancy and temporal redundancy. So explain how temporal redundancy compresses a video. Okay, so how does it compress a video? So if we was thinking about the run length encoding, is it identifies, so think about our beach scenario, okay? So what it does is quite simple. So it uses, could say uses RLE to, so it gets the similarities, for example, and it identifies the scenes or the images, or say the images that are the same, and then simply records the differences. Okay, right, okay, so I think basically if you used to answer the questions along those lines, you should be able to get all 6 marks there. Okay, so let's put this back on slideshow. So I hope you gave these a go as you was going along, and there we go. Okay, so here's the answer. The data from a single frame is split into 2 separate fields. One field has data for the odd numbered rows or lines, and the other field has the data for the even numbers. The odd number lines alternate with the even, and the viewer sees the data from the 2 frames simultaneously. So it produces what appears to be a higher refresh rate, lower bandwidth for half the bandwidth requirement, and then identifies pixels that do not change between frames and records only differences. Okay, so now if you have the booklet, okay, please do not forget to fill in the before and after section. Attempt all the tasks and attempt all of the exam questions and self-assess. Okay, thank you very much.